What's up, ladies and gentlemen? I wanted to push this out to you as we wrap up the second of our 2 week cycles here during our time away from school. We're getting coming close onto our second quiz here, and I wanted to just give this to you guys as sort of a review of some of the things that we've seen. All right, I'm going to be posting this right in our notes and examples folder, and that's really where we should have started. I'm not going to touch too much on this. I pushed out another screencast earlier last week, some notes and examples that I went over. Again, all should be pretty self-explanatory by now. Okay, same deal with the problem sets. Excuse me, just the one problem set. We had the momentum and impulse problem set where you should have made your submission. I did post the solutions right here if you were stuck. I didn't get a ton of questions on those, so I'm assuming that means that we are doing pretty well. I know this is a simpler section as far as the math goes compared to, say, like the projectile motion stuff that we were working on. I mostly wanted to touch on the two gizmos that we should have seen, and I lied. I am going to get back to a small section of the notes that I think some of us might have missed. So, first, let's look at the gizmos. The first one, we were playing around with a car, and we were looking at crumple zones with collisions. We have some sort of crash dummy here, and we were first learning about our momentum equation and our impulse equation, right? Momentum is equal to mass times velocity. So we can change the different masses of different cars. I could change how fast the car is going. That's going to give it a different amount of momentum. Okay, and then I also had you guys play around with the different rigidity. There it is. The rigidity of the crumple zone and the safety cell and things like that. And you can also change um, how long it is. And as you went into the actual crash test, you should have seen, considering that our impulse equation was J is equal to F times T, the force multiplied by the time. As this time gets longer, that allows the force to get smaller. That's part of why we do our egg drop project while we are in school, obviously. If you can make that collision longer, you are going to make the force on whatever, in this case, the car is carrying, whatever people are inside the car, the force is going to be smaller. So the longer the time of the collision is, the less the force exerted will be. Okay? And that is a big thing that I wanted you guys to see here. If I can make this time longer, the force is going to be smaller, right? And I should have been able to see here on this last results tab that gives me, I thought it gave me, maybe it just gives you the time here. Oh no, it doesn't go away. My bad. It gives you the time here. It tells you the forces that were exerted on the crash dummy, and what likelihood was there that that crash dummy would have survived. And this is why we consider things like momentum and impulse. Okay, so again, that's the big thing you should have seen there. We then got into the second gizmo. Okay, get that up and launched. All right, and we were unable to spend as much time on the conservation of momentum. Okay, and I'm going to take a small sidebar here, and like I said, I want to get back to some of the notes that I think that we missed. And I say that because I unpublished some slides here. You can see uh, some of these are, I must have this open somewhere else. Not a big deal. I unpublished some of these slides. So deep down at the end here, starting at slide 28 and all the way through 33, 34, I wanted to talk about the conservation of momentum and how that applies to a collision. Okay, and just like the conservation of mass when we're talking about balancing equations, or the conservation of energy, that which we'll talk about starting next week, momentum is something that's conserved as well. So when two objects collide, they have momentums before and after the collision. So when we isolate that system, and like in the Gizmo, the system would just be these two gliders, is what they're calling them. Okay. So that is the system. They have a momentum at the beginning and a momentum at the end after the collision. Good example of this is like if you picture standing on an ice rink, right? We can imagine that ice is pretty slippery, right? And let's say that you're holding a medicine ball, which is like a really heavy basketball, if you're not sure what that is. If you were to try to throw that medicine ball standing on a sheet of ice, you are going to essentially slip backwards, because you don't have anything to push off of. Excuse me a second. I'm getting a phone call. This can wait. So right here, whoops, sorry. Right here, everything's not moving, right? We know that momentum is mass times velocity. If my velocity is 0, the momentum is 0 here, right? Once I push this ball away from, once she pushes this ball away, that ball is moving. It has some momentum. So that means that she is going to have to cancel that out by moving in the other direction, okay? I wanted to mention these equations. Um, we didn't put them into use very much. I didn't quite. I didn't think this was worth our our time to try and tackle. Especially, this is another trickier section here. And if we can wrap our heads around, excuse me, momentum in itself, we can build on this later if you should need to. So I opted to skip the problem set for these two equations, but we have two different types of equations because the concepts are still important and we should have still seen them in the air track gizmo. We have two types of equations. We have elastic collisions and we have inelastic collisions, okay? And elastic collisions are when they do not stick together, and this means that they bounce. All right, and inelastic is when they do stick together. Okay, and you can have the reverse of an elastic collision, excuse me, in that, like, if we get back here, this would be the inverse of an elastic collision in that here, these two objects are stuck together, and here they are not. So we can flip this around if we should need to, okay? But really, these two equations are just expansions of the same momentum equation for different objects. We have the mass and the velocity of object number 1 plus the mass and the velocity of object number 2. You see a little prime here. And that's just notating that this is the velocity after the collision and this is the velocity after the collision of the second object. Okay, so if I consider the momentum of these two objects before and these two objects after, they will be equal. And that's what we should have seen here. A really good example of this is, let's say I put my masses at the same, I put the mass of the gliders equal to each other. I put the velocity of one of them at 0, and we'll leave the velocity of the other at 5. If I press play, when these collide, I can see I started with the velocity of glider 1 at 5 meters per second. When they collided, that same velocity transferred to the second object. They have the same mass, and you guys were able to come up with your own situations. I might have a case where I have one object that is way more massive, and in that case, it's going to give the lighter object a much smaller velocity, right? I mentioned, excuse me, I asked you at the end there why it's important to wear your seatbelt, right? If you're to get in a car crash, that is an example of a collision. When you are driving along in your car, you have the same momentum as your car because you are sitting in the seat and hopefully have your seatbelt on. So if you were to be launched from the car, your mass is so much lighter than that of the car that it is going to give you such a high velocity. So remember to wear your seatbelts. On the other end, and again, another really good reason to wear your seatbelt. If I change this into an inelastic equation, inelastic collision, excuse me, I put my elasticity to 0. I can see earlier my I think my velocity changed to 7.5, and now it's literally cut that in half. So it's cutting the change in velocity there in half, which is a huge difference. And we're looking at very small differences in masses here. When we're talking about the difference in mass between you and your car, it's going to be a different situation. So, um, wrapping this up, just because I'm getting a little short on time here, we should have seen a couple main things. Early on, momentum is equal to my mass times velocity. Impulse is my force multiplied by my time. Okay. I got into my crumple zone gizmo where I saw that if I can increase the time of a collision, the amount of force on the person inside is going to go down. And likewise, if I can make a collision inelastic or make sure that they stick together, I can also reduce my change in velocity. Okay, I tried to gear this more towards the idea around safety in a car because it's very relatable to you guys, and I also want you guys to be safe too. So I'll be posting the quiz early tomorrow morning. Shoot me any last minute questions. Remember, do the formatives first. I'm giving them to you. I'm writing the quizzes right about them. I'm trying to help you guys out. I know this is a tough time. It's getting nice out. Hopefully, we're getting a little bit of fresh air. I miss you guys. I wish you guys all the best, and hopefully, we'll see you soon. All right. Let me know if you need anything. See you guys.